Okay, hi guys, it's Mrs. Millicent. Okay, this is section 6.2, transforming and combining random variables. I'm going to do 3 videos, one for transforming, which we're going to do first, then I'm going to do one for combining, and then I'm going to do one for transforming and combining together, okay? But again, transforming, you already know how to do this. You know how to transform data. We've already done this, okay? Back in chapter whatever, when we wanted to transform data like convert it from feet to miles or inches to centimeters or add 10 to every data point. We saw how it affected the center and the spread. Remember, the shape never changed and the outliers never changed. But the center, which could be the mean or the median, were impacted by everything: multiplication and division and addition and subtraction. So every kind of transformation impacts the center. Okay, spread, which was standard deviation, range, and IQR, was only impacted by multiplication and division. Okay, well, for random variables, we're only going to be really concerned with mean and standard deviation, but these same rules apply. So let's just look at this example. Again, I want to do a continuous and a discrete example. And again, continuous is usually a normal curve. So again, nothing new. So in a large introductory statistics class, the distribution of raw scores on a test X follows a normal distribution. Okay, so I'm going to put X. So normal distribution of a mean of 7.2 and a standard deviation of 3.8. Okay, so these are test scores. A professor decides to scale the scores by multiplying the raw score by 4 and adding 10. Okay, so I'm going to say R is my new random variable, which is the raw, not the raw score, the scaled score. X is the raw score. Why did I call it R then? Let's make it S. Okay, so the scaled score is simply going to be 4 times the raw score plus 10. Okay, so let's see, if some kid got a 20, 4 times 20 is 80, plus 10, they got a 90. Okay, so I could do that for all my individual scores, and then find the mean and standard deviation of all my scaled scores. But I don't need to do that. I can work with the mean and standard deviation of the raw scores and just transform it because I know this. Okay, so to find my mean of X is 17.2 and my standard deviation of X is 3.8. Those are my raw scores. Okay, for my scaled scores, I want to find the mu of S and the standard deviation of S. Okay, so I know all I have to do is multiply the mean by 4 and add 10, standard deviation multiply by 4, but do I need to add 10? Of course not, because standard deviation is not impacted by addition and subtraction. So if I take 4 times the mean and add 10, I have it written down. 78.8 is the new scale, the average of the scaled score, and that will vary by 4 times 3.8. And those scores will vary by, where am I? 15.2. Okay, so transformation isn't different. It's the exact same thing. I'm just putting the word random variable in here. Matter of fact, did I even have the word random variable? I didn't. All I had was that capital X. Okay, no big deal. It's the same stuff. So again, the raw scores, the average was 17.2 and it varied by 3.8. But then when we scaled it, the average score was 78.8 and that varied by 15.2. Okay, and again, that's a big variance. That's a letter grade, just saying. Okay. The question is, what's the probability that the randomly selected student has a scaled score of at least 90? Well, if the raw score is normal, the scale score is normal. Okay, so I can just throw this on a normal curve. Gotta love normal curves. So the mean of my scaled score is 78.8. I'm concerned with a score of at least 90. Okay, so at least 90 means 90 and above. And we know what to do from here. Well, z-score. See, I told you z-scores were never going away. And what is that? 0.737. Then, of course, I'll do my normal CDF in the calculator. 0.737 to infinity. Normal CDF. 0.737 to infinity. and I get 0.2306. Okay, so there's about a 23% chance that a randomly selected student's going to have a scaled score of at least 90, okay, because the average was about 78.8, okay. So again, starting with just the raw score, I couldn't put 17.2 here and compare 90. That would be a lot of standard deviations, and the probability would end up being 0. So I have to transform the raw score into the scaled score, but transformation is exactly the same, okay? All right, so this is continuous. Let's do one with a discrete random variable, and you'll see it's pretty much the exact same thing, sort of. Okay, high school students all across the country, can earn college credit while in high school. So the number of college credits, X, there's my random variable, that a randomly selected high school student earns while in high school has the following distribution, okay? Majority of the kids, 52% of the kids, don't get any college credit while they're in high school, okay? So my distribution is definitely right skewed. About a quarter of them get 3 credits, and then 15% get 6 or more credits, okay? So find the expected number of college credits earned in high school and how much that varies. Okay, we can do this. That's just the expected value. So that's my mean of X and my standard deviation of X. So of course I'm going to calculate the mean by hand, which is just my weighted average. So each random variable times its probability added up. And again, I always do the mean by hand, and I throw these in the calculator to get the standard deviation, and I check my mean. Again, I never put the 0 in the calculator because I don't need to, because 0 times anything is 0. Hopefully I'm typing all this in correctly. 5. I do have my answer somewhere. Okay, 2.67 credits. So I would expect a high school student to earn about 2.6 college credits while they're still in high school. And let's see how much this will vary by. So remember, list 1 is my random variable, list 2 is my probability. So 0, 3, 6, 9, and 12. Then I'll put in the corresponding probabilities. Okay, and then I run my one variable stat. My random variables in list 1, my probabilities or my frequency are in list 2. Okay, list 2, alpha 2. And we'll check my mean, which is correct, and my standard deviation is 3.52 credits. Okay, so again, a typical high school, a randomly selected high school student will typically earn about 2.67 college credits, and that'll vary by about 3.52 credits. Okay, now that's just a straight expected value. There's no transformation. Here's how I want to transform it. Now the tuition for high school students is $25 a credit, okay, which is a deal, okay, in addition to a one-time student fee of $10. So we'll call the random variable C the overall cost for a randomly selected high school student to earn college credit. So let's find the expected overall cost. So I want to find the mean of C and the standard deviation of C, okay? So basically, if they earn 2.67 credits at $25 a credit, it makes sense. I would just multiply 25 times that. Okay, so that makes sense. 25 times 2.67. And then they always have a one-time fee, so I got to tack that $10 on. So a typical high school student, let's see, throw that in the calculator, will spend $76.75 earning their college credit while in high school. Again, quite a bargain when you compare it to what a college student pays. Okay, now to find the standard deviation, thinking about transformation, I definitely should multiply the $25 per credit times 3.52 credits. But again, for transformation, standard deviation is not going to be impacted by that addition. So I only need to do the 25. So that is $88. Okay, so a typical high school student earning an expected 2.67 credits is going to pay on average $76.75 for those credits. Okay, the credits will vary by 3.5 2 credits, and the amount of tuition will vary by $88. Okay, so you'll see transformations are exactly the same. Mean is always impacted by multiplication and addition, multiplication, division, and addition, subtraction. Standard deviation only worries about multiplication. I don't have to worry about that $10. Okay, so that's transformation. It's really not different than what you already know. Okay, so I hope this was helpful, and I'll see you at the next video.